Hi, this is Mr. Ward, and I'm going to do a short video on just introducing the idea of sequences. Now, sequences are simply series of numbers, like a list of numbers. It could go on forever, and they may or may not follow some sort of rule. We're going to focus on the ones that do follow a rule, because those are a little easier to work with. And there are going to be two general types of sequences that we'll be talking about in this section. Arithmetic sequences, which closely relate to linear thinking, and geometric sequences, which closely relate to exponential thinking. So we have here a sequence 3, 5, 7, 9. We would consider the 3 the first term, the 5 the second term, and we're going to refer to terms, the numbers as terms, and it matters what order they're in. These 3 dots means it goes on forever. It's an infinite sequence. We might refer to the terms as elements or members, but they are ordered and they are designated an index of some sort. So first, an index being this is the first one, the second one, third one, the fourth one, and so forth. And so you look at these numbers and you think, is there a rule? Well, there's sort of a general conceptual rule, which is these are odd numbers starting with 3. But we didn't include all odd numbers. We started with 3. We could have started with -17 if we wanted to. But we started with 3 as the first number. So you could come up with a rule for this, which would be something along the lines of starting with 3, you add 2 to get the next number. And you always add 2 to the last number to get the next number. And we're going to learn about how to formalize these rules as equations going forward. Let's take a look at a few sequences here. So here are some examples I used in the notes. 3, 7, 11, 15, 19, then 1, 1/2, 1/3, 1/4, 1/5, and so forth. Let's think about what could be a rule that's being followed. Well, if you look at 3 to 7 and 7 to 11, 11 to 15, 15 to 19, there are things you could do. You could do some method of comparing the numbers. One method is to subtract the next number, subtract a number from the next number. So 7 minus 3, you get 4. 11 minus 7, you get 4. 15 minus 11, you get 4. And 19 minus 15, we get some sort of repeated plus 4 happening. So this is what we would call an arithmetic sequence, which is connected to linear thinking. There is a repeated plus 4 happening, starting with the number 3. In the next one, what seems to be going up is a denominator. 1 could be treated as 1 over 1. Then we got 1 over 2, 1 over 3, 1 over 4, 1 over 5. So you could maybe predict that the 17th term is 1 over 17. Each number is its term number, its index. It's 1 over the index, I should say. So the 65th term would be 1 over 65. And that's what's happening. This is a reciprocal kind of sequence, and I'm not going to deal with that right now, but that does show up in the rational functions unit. The next one, 64, 32, 16, 8, and 4. In this case, if you subtracted 64 from 32, you get -32. But you subtract 32 from 16, you get -16. So we're not getting the same thing. But -32 and -16, and then we get -8 if you do 8 minus 16, and -4 if you do 4 minus 8. It seems like there's some sort of halving happening here. If we instead were to divide, you could compare by dividing instead of subtracting. 32 divided by 64 is 1/2. 16 divided by 32 is 16 32nds, which is 1/2. 8/16 is 1/2. 4/8 is 1/2. Or you might have thought about it going the other way. What do I do to 64 to get to 32? I have it. I have 32 to get 16. I have 16 to get 8. I have 8 to get 4. So we are halving repeatedly. So you could think of this as repeated multiplication by 1/2 or repeated division by 2, starting with 64. And this would be a geometric sequence. And it has a timesy way of counting. We are counting in 1/2 times steps. Each new number, starting with 64, is half the last one. Okay, and then the last one we've got in this list, 1/3, 1, 3, 9, 27, 81. Again, subtracting doesn't give you the same thing. But if you look at what would I do to 1/3 to get 1? Well, I'd multiply it by 3. I'd triple it. What do I do to 1 to get 3? I'd triple it. I'd triple 3 to get 9. I'd triple 9 to get 27. I'd triple 27 to get 81. So we have a repeated multiplication of times 3. We are repeatedly tripling, starting with 1/3. And so you could set up what's called a geometric sequence for this one and the one before, because they are both repeatedly multiplying. And the rule you could come up with is some sort of times 3 each time. So, and you'll want to, of course, you can take a look at, what I came up with in the notes as examples, if you like to refer back to that. We can go on and take a look at a few more. So here's some other sequences. This one is a weird one. 1, -1, 1, -1. It's just going to be 1, -1 forever. And what's happening here? I'm multiplying or dividing by -1 repeatedly, starting with the number 1. 2, 8, 18, 32, 50, 72. Well, this one is a quadratic one. So what I'm doing is I've got 2 times the term number squared. Notice that you've got, this is 2 times 1. This is 2 times 4. This is 2 times 9, this is 2 times 16, this is 2 times 25, and this is 2 times 36. Basically, it's doubling a list of square numbers, 1, 4, 9, 16, 25, 36, and so on. So you could treat this as a quadratic sequence where it's 2 times the term index squared. So 2 times 1 squared, 2 times 2 squared, 2 times the square of 3, 2 times the square of 4, 2 times the square of 5, 2 times the square of 6. And then the next one is a very famous one. It's known as the Fibonacci sequence. So this one, it's hard to come up with like an equation for it. It's easier to come up with what's called a recursive rule, which is a rule that refers back to early terms. So we start off this one. The basic rule would be, and you can just think about this for a second. You got 0, 1. 1 is 0 plus 1. 2 is 1 plus 1. 3 is 1 plus 2. 5 is 3 plus 2. 8 is 3 plus 5. 13 is 5 plus 8. And then the next one would be 13 plus 8, which would be 23. And then it would be 13 plus 23, which is 34. And then 23 plus 34. Actually, I think I messed that one up. But at any rate, so, yeah, sorry, 21. 8 plus 13 is 21. And then 21 plus 13 is 34. And 34 plus 21 is 55. I knew I had messed that up because last year when I was 55 was a Fibonacci birthday for me. So I knew it couldn't possibly be not 55. At any rate, what you would do is you would set up a rule, something like this here. So you start with 0 and 1, and then each number after 0 and 1, the first and second terms are 0 and 1, and beyond that, you add the previous 2 numbers. I've included a really fun video series here that is worth watching for education and just for fun. Vi-Heart Math in the Greenhouse Video Trilogy, which explores that. 4, 5, 6, -3, -14, -17, 0, 31 will take some work. I'm going to let you think about that one. But that's just sort of an introduction to some of the types of sequences. And I will remind you that we keep track of the parts of the sequence. We number the terms in the sequence. And this allows us to create equations to describe their patterns, which is going to be the subject of my next video.